Hello, here we are with another circuit analysis, this time one without any numbers, just to show that we can do algebra as well as any mathematician can do. So this is from an NJA paper, that's a Cambridge University Engineering Assessment entrance exam paper if you want to go to Cambridge and do engineering. So we've got a simple setup here of three resistors, two of them in parallel, and then that pair connected in series. They're of different resistances, non-zero, R1, R2, R3, and we've got an EMF of V. So which of the following statements must be correct? Right, so we start without having to do a calculation. So are the currents through R1 and R2 the same? Well, no, they can't be, because the current's going to split when we get to this parallel part, so that's not going to be true. Currents through R1 and R3 the same? No, for the same reason. Currents through R2 and R3 the same? Well, I mean, they could be if they had the same resistance, but it says that this must be correct, so it's not going to be that one. The voltages across R1 and R2 the same? Well, they don't have to be. I mean, again, they could be, but they don't have to be. We've got the same argument for the next one, because it's doing R1 and R3 again. Are the voltages across R2 and R3 the same? Yes, we finally got one that works, right? So that's a nice starter. Now, I mean, I've cut out the options on these, so they're all saying here which of the following expressions gives the current through the voltage source. But I've chopped those out just to create some space. So let's just work out what the current is through the voltage source. So that current is going to be equal to V divided by the total resistance of the circuit. So our total resistance is going to be, well, we got R1, and then we need to add on, and we can't do any of our quick tricks on adding up this parallel branch because we don't know what R2 and R3 are going to be. So 1 over R2 plus 1 over R3 to the minus 1. So when we add those up, we're going to get what, R1 plus, that's going to be R2, R3 over R2 plus R3. And then we need to add those, which means we're going to get, what are we going to get? We're going to get R1, R2 plus R1, R3 plus R2, R3 all over R2 plus R3. So that's just working through what would be a really simple calculation if we had numbers, but we're just showing we can do it all without numbers. Oh, that's just the RT bit. Yeah, of course, we need to get what the actual current is, don't we? So we need to do V times 1 over that. So that will mean, I'll just write it here just to save a bit of space. V times R2 plus R3 divided by, well, all of this stuff. R1, R2 plus R1, R3 plus R2, R3. Right, so all good there. So that's done part B. Right, part C, R1 and R2 are now fixed so that they're the same as each other. Which of the following expressions gives the power that is dissipated by resistance R3? Right, so now our R total then for part C, what are we going to get from it? So they said, what is this? R1 is equal to R2. So let's call it all R1 then. So we've got R1 squared plus R1 R3. Oh, so that's going to be two lots of R1 R3 divided by R1 plus R3. So that is going to be, well, you could factorize an R1, I suppose, at the start, couldn't you? But I'll leave, yeah, let's do it now, I've said it. So R1 times R1 plus 2R3 divided by R1 plus R3. So that's our total resistance. What are we trying to work out? Power dissipated in resistance R3. Right, so we're going to have to work out our parallel resistance, and then we'll be able to see what fraction of the total we're going to have as our potential difference. So for the parallel section of R2 and R3, that means we're gonna, well, that's this bit here, we've already worked it out, but now we're calling it R1 rather than R2. So that's R1, R3 over R1 plus R3, because of course our EMF V here is going to be split in proportion to the resistance in each section. So if we want to get the potential difference across resistor 3, it's going to be our R parallel divided by the R total, because that's our fraction of the total resistance that's on that branch. So that's going to be the fraction of the EMF that we're going to have. So that is equal to, so RP divided by RT. I'm just trying to see what's going to happen on this. We're going to get some things cancelling. I'm going to have to write this out because I've got it in too many different places. All right, so R parallel, so that's R1, R3 over R1 plus R3. And then we need to do divide by RT. So that's going to be multiplying by R1 plus R3 over R1, R1 plus 2R3. Right, so we do have a lot of things cancel. That, and that. And then we need to multiply by V. This is not leaving me much space for the rest of the question. So I'm going to put the answer over here, because that's just going to be V times R3 divided by R1 plus 2 lots of R3. So again, okay, it's just emphasizing the need for good algebra, but it's another way then of looking at this, the way we're dividing up the EMF. You know, quite often, you know, we're thinking, okay, well, let's divide these into proportion and say, well, we've got, you know, R1 in proportion to R parallel, and then we divide up V that way. Well, of course, we can do it a different way and say, well, what is our total resistance? And then we can just do fractions. You know, our PD across R1 is going to be R1 divided by R total. You know, it's just a different way of doing the same thing. You know, this is exactly what we've done here. Of course, multiplied by the EMF. What we've done here. What fraction of the total resistance is in the parallel branch, and that is going to be the fraction of the EMF that is the PD across that branch. Okay, so that's the end of part C. Oh no, it's not. No, because no, just looking at it, yeah, they want the power. I only got as far as writing down what the voltage is. So this is our PD across resistor 3. That's our V3. So we need the power, which is what V squared over R. So we need to square this and then divide by an R3. So we're going to have V squared R3, because the other R3 will cancel, divided by R1 plus 2R3 all squared. Kind of squeeze that in because I've still got to do part D, which I'll change colour for. For the case where R1 equals R2, which of the following values of R3 maximises its power dissipation? So we're going to have to do some calculus. You may find it helpful to use the fact that any value of R3 that maximises P also minimises 1 over P. Right, so they seem to be pushing us to it being easier to do the calculus if we do the reciprocal here of P. So let's go with that then. So 1 over P is going to be, well, we can see what that's going to be if we just flip that over. We're going to have to, and then differentiating that. Actually, if I expand the bracket, then, yeah, things might cancel. Right, so I'll expand a bit at the top then. So that's going to be R1 squared plus 4R1R3 plus 4R3 squared. So that's expanding out the bit in the bracket. That's then going to be divided by V squared R3. So yeah, we're going to have, yeah, we can cancel some R3s. Okay, we'll split it onto different terms. We've got a 1 over V squared. Then we're going to have an R1 squared over R3. What's that? A 4R1. And a 4R3, which I can't quite fit on, but there we go. We just squeeze it on the next line. So now that's what we need to differentiate, and at least it's in 3 separate terms. So that's going to be a bit easier to do. So we're going to be doing d of 1 over P by dr3, bit of a unusual way of writing out your differential there, but that is what we're working out. So the 1 over V squared is going to stay where it is, and then we can just differentiate the bits in the brackets. So that first term is going to be minus R1 squared over R3 squared. The next term is going to be 0, and the last one's going to be 4. And we're going to need that to be equal to 0, which means that we need minus well, the bit in the bracket has got to be equal to 0. So that means we're going to have the R1 squared over R3 squared has got to be equal to 4. What am I trying to work out? The value of R3 that maximizes the power. So we just need to make R3 the subject. So that's going to be R1 over 2. R3 equals R1 over 2. Right, yes, it would have been nice to have a bit more space on the page. But you can see the process that we're going through there. It's just as well they pushed us to this minimizing thing, because I think we might have been stuck in a bit of trouble having to differentiate that otherwise. Yeah, it's quite a lot to deal with. I mean, we can see that this is going to be a minimum, because if we differentiated it again, then we'll end up with a positive value, because the minus sign, this negative power we got on the R3 is going to cancel with the minus sign we've got there. And because R1 and R3 and V are all positive, we end up getting a positive second derivative, which means we're going to have a minimum. So that's why we know that we can just solve this and say, yeah, it's definitely a minimum, because it's the only way it can end up. But yeah, hopefully that's sort of made some sense, even though I've had to squeeze it onto the page a little bit. But it's useful to go through these questions like you get in some mechanics papers where they don't give you any numbers, because then it's really showing that your algebra is up to scratch, rather than you're always having to sort of break off in order to simplify things by putting in the numbers that they've given you. So it's worth working through this. If you don't get this sort of question first time, go through it again. Or even dig up the this is off the 2016 NJA, the second paper with the long questions. That actually then gives you the different answers that you might be working towards. So that's another thing to help as an intermediate step if you're working on your algebra. But there's nothing much here that if you've been through it a couple of times, you should be quite slick at working all of this out. Because all we're really doing is a whole load of fractions and then a little bit of calculus at the end. So yeah, it's quite a nice one from that point of view. And it started off with these basic ideas here of really this is making sure you understand Kirchhoff's laws as to why these things aren't necessarily true in cases A to E. It's only got to be true for part F. So yeah, quite a nice question all in all.